Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, good morning everyone. Welcome to this talk. It's my pleasure to introduce Suprit Krishna Rao. He's been with us as a summer intern over the past 12 weeks, working on ultrasounds. He's a master's student at the Worcester Polytechnic Institute of Robotics Engineering. And without further ado, the floor is yours.
Thank you, Hannes. Very well. Good morning, everybody. The audio team, Dr. David Heckerman, Mark Keith, Dr. Ivan, and Hannes and everyone. So basically today I will be presenting to you the work that I did with my mentor, Hannes Gamper, at Microsoft Research Redmond, Washington, in the last 12 weeks. So we attempted to basically develop hardware and algorithms for Ultrasound-Doppler Radar, and the primary objective was basically imaging range and velocity profiles of objects of interest in the field of view. So let's see in a more formal way what the objective was. So given a system, we wanted to image and estimate right around the system, that is basically a 360-degree horizontal field of view. In that field of view, we wanted to estimate and measure and estimate target's position and velocity relative to the user. And why would anyone do that? Probably for such situations wherein with increasing technology or with more number of disabled people, we need more intelligent systems to be actively sensing the ever-changing environment for us. And this is one typical case wherein a user is happily listening to some music while walking on a busy road. That's definitely gonna come in the very close future, and he need not really worry about the vehicles approaching him, because such a system aims to warn him about these targets. So the underlying principle for this system was basically Doppler Effect and Time-of-Flight. And just to give you a quick illustration of what Doppler Effect really captures is basically when you actually transmit a signal, there is actually a change in frequency when there is relative motion between the source and the receiver. So in this case, the source would be the user, the object would be probably the car or the target, and again the receiver is present with the user. So let's take a look at why we chose ultrasound to achieve this task, whys and why nots. And firstly, ultrasound is very low power consuming, and since it's not very high frequency, it's about 40 kilohertz, high frequency components are not pumped into the circuit, and so this is basically why the electronics is really cheap when you're designing an ultrasound system. And small form factor is a great advantage, because it offers a great choice for mobile devices, because as you can see in the later slides, a transducer, an ultrasound transducer is millimeters, or it's really small. So even after using probably an array of transducers, the form factor will not have really blown up. And most important thing again is it's outside human perceptible range. So if the device is being used by the user, it won't really interfere with his normal day-to-day activities. Well, works very well in indoor, outdoor, well lit, and you don't need light. So it's as against any other, for example, cameras or something. So it doesn't need illumination. It's active sensing, and it works equally well indoor and outdoor. And array signal processing basically can be leveraged to get a 360-degree field of view, which we have in this system. And the responses of these transducers and receivers are not super directional, so we need beamforming to really improve the spatial angular resolution of our sensing. And we can leverage active time-of-flight sensing. That is basically how the transducers work to get a range or depth estimate. And again, this is not really available in passive sensing devices like cameras. And to cap it all, basically we attempt to use Doppler effect to get even velocity profiles of targets in the field of view, and this is every frame. So this is not across several frames, or it's not. So every frame we have an estimate of the velocity and the distance. That was the attempt. And so the immediate question to ask again is, why not use cameras? Well, we don't get depth information, and also we need illumination because it's not active sensing. And okay, yeah, we get depth information using stereo cameras, but why not that? So they require global shutter, and this often shoots up the price of the cameras and the entire setup. And stereo vision cameras require precise alignment and calibration. This is really time consuming, and even after sufficient calibration, the depth resolution or the depth accuracy is not really fantastic. So one might say, to avoid these calibration issues, why not use a commercial stereo camera setup like Bumblebee or Asus? They actually require very computationally intensive processing algorithms like sum of absolute differences or sum of squared differences, and these often necessitate a GPU, and that again shoots up the power requirements and the cost. And again, no 360-degree field of view. Well, to get 360-degree field of view, we can use LIDARs, but they are expensive and power hungry. How about Kinect? Kinect manages to solve many of these issues apart from 360-degree field of view. But well, 36 watts power consumption, and it requires a fan to keep it from overheating. Keeping all of these in mind, we decided to use ultrasound, and we'll see more about that. So we actually have to be objective and take a look at the other side of the coin also. So limitations and challenges of ultrasound. I guess the list is pretty long, compared to the previous slide. So challenges are a lot more. Firstly, calibration is still required, and it often demands anechoic conditions. An off-the-shelf researcher who wants to use such an array or such transducers can't really get access to costly anechoic chambers. That's still there, and sensor responses are basically very wide angle, and this kind of affects the spatial angular resolution, so that necessitates in a lot of signal processing. And frequency, the responses are again frequency and temperature dependent because they're piezoelectric transducers. Reflections are one more challenge because you have multipath, multiple and specular reflections. Again, that necessitates a lot of signal processing. So we are moving closer and closer to some of the major issues that we experienced. So basically, maintaining good signal to noise ratio, achieving practical frame rates, and making sure that the device operates over a wide range. So some of the constraints that control these parameters are basically power, pulse width, and attenuation of ultrasound in air. So power basically is, we ultimately increasing the power would increase the distance and the range, but that would again result in overheating. So one can't really crank up the power after some point of time, beyond a point. And pulse width improves SNR, but again kills both frame rate and range. And of course we have more than 3 dB per meter of attenuation of ultrasound signals in air above 100 kilohertz. So these are, so basically it calls for some sort of an optimization between all of these. So these are basically the questions at hand. How to increase SNR, achieve good directivity, high frame rate, and prevent overheating. And again, estimate velocity and in a single shot. That has not really been done.
So we have really good proof of concept flying around down on like some Amish bats, basically. So what's their range?
Bats, they're in the same range. There is 40-45 kilohertz and can go 5-ish, 10 meters max.
10 meters? That's pretty good.
We went further than that.
Yeah, I see. Okay.
So I'll just walk you through the organization of this talk very quickly. So we dive into, we present a literature review, and then take a look at the problem formulation and give a small background about Doppler effect and how we can use it, and for signal design and estimation. And then we will conclude the talk with presenting the current approach, progress to date, and results. So one can actually notice that right starting from early 1950s to 2012, 2013, and now 2015, researchers have invested a lot of time and resources on trying to make use of ultrasound. So it basically tells a story, because man has not yet rejected ultrasound, because for all these years continuous progress has been happening and more applications have been coming up. More recently, you can see that ultrasound imaging was actually considered for HCI tasks like gesture recognition, activity, speaker, gender, age, gait recognition, all of these smart home environments. So ultrasound has stayed with us for a long time. And micro Doppler signatures, these are particularly interesting applications wherein you basically so every small parts of a moving object results in a Doppler shift. So, and that is quite unique. That's what the researchers have reported, and probably feeding the signatures into a deep neural network can help us learn the signatures and do some recognition. And from a range detection perspective, again, work has been happening since 1997 until 2014, and in fact, the last one that you see here, that was the prototype developed by the previous intern, and we made use of it sufficiently for our preliminary evaluation and testing. And this was again carried out under the same group under Dr. Ivan Tashev. So let us see. Let us take a look at the problem formulation, that is the Doppler radar. Like I mentioned before, this illustrates the concept of Doppler radar. To get more technical, to be more formal, received signal is basically stretched and compressed when the target is actually approaching or receding, and ultimately this is what we aim to measure. So typically a tone or a pulse or a chirp is emitted to ensonify the surroundings, and we make use of a chirp signal that goes from 38 kilohertz to 42 kilohertz, and reflection of a moving target at a velocity v is basically represented by SR of t, and you can see that the signal is actually stretched and delayed. So the stretch gives us an estimate of the velocity of the object, delay gives us definitely the distance, basically the time of flight. and these stretch factors are calculated as a ratio of c plus v by c minus v, where velocity's direction matters, the plus or minus, and time of delay is basically the time required by the ultrasound to reach the required range and get back. So essentially we are trying to estimate these two factors, that is the stretch factor and the time delay, to determine the range and velocity. So particularly from the literature review, this one particular paper gave us some insights about signal design and estimation. So they proposed something called as the wideband cross ambiguity function, which basically is a 2D coupling. It's basically a 2D representation that couples the delay and stretch factors. So effectively, as you can see there, it's basically the cross correlation between the transmitted, the received signal and time delayed and stretched version of the transmitted signal. And some points to be noted is basically for all practical purposes, the integral is over minus t by 2 to plus t by 2 basically, because our system is band limited, so we don't need to do the overall integral. And like I mentioned, it's basically a 2D representation of the correlation, and the ultimate task is to estimate these two coordinates in that 2D representation here. So some insights from the same paper about signal design. We see that LFM stands out as it gives better resolution for estimating the two parameters. This is the Doppler stretch domain, that is the time delay domain, and you can see that the Gaussian signal would be very, very ambiguous as against LFM. Some more results in favor of LFM from the literature. We see that we get better resolution using the LFM. So we implemented the signal basically that you see here, the time domain version, the frequency domain. Basically the frequency sweeps from 38 kilohertz to 42 kilohertz, and the pulse width is about 5 milliseconds. Some of the parameters that we considered while designing the signal to be transmitted is basically we are sampling at 192 kilohertz. Our center frequency is about 40 kilohertz because our transducer's resonant frequency is basically around that range, around 40 kilohertz. Max range we are considering is about 9 meters. Currently this can be changed, and pulse width is about 5 milliseconds. So one interesting thing to note here is the sequence width here. It's 10,076 samples. That basically these are the samples that are represent the duration the sound takes to basically do a round trip to the max range, and sequence width basically decides the max range, and all of this is basically dependent on the speed of sound. So taking a look at the implemented pulse train that we are pulsing out from the. Thank you.
Does it work?
It kind of does. You'll see the results. Thank you.
I can't wait for the answer.
Thank you. So looking at the pulse train being transmitted. So this is basically, this represents one block. We have 8 channels and basically 8 channels of transmitters and receivers and 20 frames. So 1, 2, that goes up to 20. And we make use of PlayGraph to basically interface with the sound card. We generate the signal in MATLAB. We interface with the device using PlayGraph to play and record the signals. So going into some more detail into the estimation framework, that is the wideband cross ambiguity function. I just want to remind you that it is basically a 2D representation of the transmitted and the received signals. So if you can see here, so this is actually the stretch factor like I mentioned before. We decided to go for the following stretch factors based on these constraints. We decided to basically measure velocities of objects from 20 plus or minus 20 milliseconds. So meters per second, extremely sorry for that. That is about 40 miles per hour, and directly deriving from that formula we get the stretch factors, and with regards to the number of stretches, that basically decides the resolution of this ambiguity function that you saw. So for a sample, for example, for a stretch factor, for the number of stretch factors of about 31, this is illustration of the stretched LFM. You can see that across 31 stretches it is stretched in time, and implementing the ambiguity function and testing it for LFM for the ideal case, that is 0 Doppler shift and 0 delay. This was the response that we got, and as you can see it's pretty high resolution in this domain, that is in the stretch factor domain. And we tested our initial algorithms on the previous prototype that was available and built in this group, and this is how it looks. Basically you have an array of transducers, microphones, and testing on this setup gave us our first light, that is some results. As you can see, the plot to the left is basically the cross correlation that gives us the measurement of the distance. So you can see that there is a strong peak at around 0.6 meters, and you can exactly see that this cross here, which represents the maxima of this function, is again at around that range, that is 0.6 meters. And one more thing to be noted is the speed, since this is both single shot estimation of both the velocity and the delay, the range. So the speed is more to the negative side because the object was really approaching the setup in this case. So basically what I mean is, let us assume that, this is actually the setup that we were considering. So there was a Kinect facing the setup, and this 2D this plane surface was moved backward and forward in one dimension across this dimension, and this represents the depth map of the Kinect. So we just measured we monitored the depth value at the center of an ROI that represented our object, and that's how we got this plot. So if you can see the overlaid data of the Kinect depth estimate and our system's depth reported by our system, you can see that the slope, which represents the velocity, is quite consistent. Of course there is an offset because there was a bias in the arrangement between the Kinect and our setup that can be corrected for. So diving into the hardware design, basically we have piezoelectric transducers that we use, and this is how the prototype looks. As you can see, it's basically a low form factor device of about 50 millimeter diameter and height of about 100 millimeters, 110 millimeters, and we have the receiver array, the transducer array here. So taking a look at the system architecture, we have this basically is the system architecture. We have our microphones, we have preamplifiers, we make use of RME to basically mix the signals that are sent and received, and it's interfaced to the system, to the computer, through a firewire, and that is going into again a preamplifier, and there is our speaker array. So this looks more intuitive than the previous one, than the previous slide. So basically, this is our test and calibration setup. We have our device, and for calibration, we made use of B&K receiver microphone, and as you can see, this is the previous prototype that was used. So taking a quick look at the IR GUI that we made use of, that was developed by Dr. Mark Thomas. So we make use of certain regions of this GUI to actually send a test signal at around 40 kilohertz, and then we measure the responses, we update the gains, and this is basically the impulse response recorded, and the magnitude response to the right. So how was this actually done? So to calibrate our speakers, we actually kept this microphone at 1 meter distance, and we pinged through all of our speakers, and the responses recorded here were basically what you saw for one channel, that is. And to calibrate the receiver setup, we used a transducer from this setup. We again pinged, and then we measured the responses using our receivers, and we recorded the impulse responses. So these are some of the directivity patterns that we observed from the measurements for the transmitter. They don't look really directional, do they? Yeah, so they don't. That was.
They are directional, but not uniformly.
Not uniform. Yeah. So they are, although they are directional, they are not really directional for about 15 degrees, plus or minus 7.5 degrees, which we are looking at. And you can see the transmitter frequency responses. One more challenge that we face, by the way, this is after calibration. You can see that they are not very well matched. So this was something that kind of created some delay in our progress, and but of course you can see that the resonant frequency is somewhere close to 40 kilohertz.
Actually, your work area is between 45 and 50 kilohertz.
Yeah.
This is where they match, and they're flat out of the resonances.
Yeah. So the receiver directivity pattern looks something like this. Again, they are quite directional, better than our transmitter, more uniform, like Dr. Ivan said.
So this is just the scattering from the cylinder, right?
That and the natural directivity of the microphones themselves. They're audio frequencies, but we're talking even just the can it's made from is going to be quite significant.
Yeah. So but the one can note that the receiver. So this is actually the transmitter that we used from the previous configuration, developed by the previous intern Ivan Dokmanic, and these are the receiver responses. So they're all quite well matched. That is pretty good, better than this. So this all this necessitates beamforming. That's the long story short. All this necessitates beamforming because we need better spatial angular resolution, and we made use of the BF GUI tool developed here again by Dr. Mark Thomas at the audio and acoustics research group at MSR, and this is basically used for generating the beamforming weights. For example, this represents the method we use for beamforming, MVDR closed form, and this basically shows the array setup for our speakers, and this is basically the metadata, basically the dimensions. So as we can see, the directivity pattern, and this is exported and stored for later use, which we will see. And same goes with receiver beamforming weights. We used NVIDIA closed form. We evaluated NVIDIA closed form method, and this is what it looks like.
Omnidirectional directivity pattern.
Yes, we used omnidirectional. So that made us go for some other method of beamforming that we'll see in the near future, because firstly our setup was, our transducers were not really omnidirectional. So these are the results from the previous two GUI slides that you saw. This is for the receiver. Looks pretty good, but still has a lot of side lobes that really catch many reflections. And with respect to transmitter beamforming, I don't need to say much. It's not really it's not very great. So all this actually made us choose a different beamforming weights estimation framework. That is, we did it through numerical estimation. We had our acoustic channel impulse responses, and this was actually the desired beam pattern that we were targeting for the receiver and for the speaker. And we actually did numerical estimation. We basically fit the curves to get this. So we are forcing
Beam pattern synthesis, right?
Based on the measured data rather than.
Yeah.
Okay.
Yeah. So as you can see, the MVDR is represented by green, desired is blue, and curve fitted response is in the red. So it is quite evident that the red ones perform much better than the green ones. That is MVDR classical estimation of the weights. Same goes with the receiver responses. Pretty good. The red ones perform pretty well, and these are all the 24 beams, by the way. Yeah. So for beamforming, we are making use of 24 beams rotating at step size of 15 degrees from 0 to 345 degrees, and these are all the 24 beams that you see. So taking a look at the flow chart of this entire system, this is basically a recap of what we saw. We have the IR GUI tool. We generate the acoustic channel responses. We get the we design and generate the desired pattern. I should probably mention a little bit about that. So this was basically the signal, like I mentioned, that generates this pattern. So we generate that signal, that pattern, and then we take the it's basically multiplication of the pseudo inverse of the acoustic channel matrix, that is basically H, which basically is acoustic channel response, and the desired pattern. So this gives us a curve fitting, and ultimately we arrive at the beamforming weights for this particular recording. So if we do another recording for another measurement of the acoustic channel responses, we need to regenerate the weights. Right. So once we get the beamforming weights, let's again traverse from here. We generate the 8-channel 20-block signals in MATLAB. We play it through playgraph, and then we segment the received signal into a matrix, a 4D matrix of, it's basically in the frequency, we convert it to frequency domain. And so NFFT, number of mics, that is 8, number of speakers, that is 8, number of blocks, that is 20 in our case. So it's basically a 4D matrix. And we perform band pass filtering on the received signal to basically reject all the noise and signals beyond our frequency range of interest. And after that, we do beamforming for the transmitters. So we have the weights from here, the received signal, and then we basically do offline beamforming. This was something that was observed in the previous internship, basically by the previous intern. He observed that leveraging the LTI linear time invariance nature of the system, he basically suggested that transmitter beamforming also can be performed offline, which significantly improves the frame rate. And then we perform microphone beamforming, as you saw before, and then we perform a matched filtering to basically again get rid of unnecessary reflections and noise basically. We perform a background subtraction, which you will be seeing in the next slide. So some preliminary results from this new device is something looks something like this. The raw map of 360 degrees across 24 beams, and we do post-processing, that is to remove the noise by using a naive approach, which is basically background subtraction. So you can see that I play a quick video here. So this was walking detection test to see if the system really detects a person approaching and slowly walking past the device. And exactly, thank you, Hannes. Among so much clutter, so basically our environment was quite cluttered. Ideally, this should have been done in the anechoic chamber, but we received the device towards pretty much the end of the internship, about when about 3 to 4 weeks were left, and there were heatsink issues, and we had to install a heatsink. So the device was actually going back and forth from the hardware lab to us. So with all this, and so that kind of didn't let us move the entire setup to an anechoic chamber and make better measurements. Well, amidst all this clutter, there is some happy news still. So you can see that for the testing, that the walking testing, this was the response. This was the response for the walking detection. You can see, of course, some more post-processing is to be done. We are currently just using naive background subtraction. We can make use of particle filtering, Kalman filtering, or any confidence-based tracking approach to basically fix the object of interest.
Actually, I think it would be interesting to see the video before background subtraction.
Oh, right. Do you want me to play the video again?
Before background subtraction, you have the raw video as well.
Right.
It's right there.
No, that's not. So this is actually how it looks. Before background subtraction, you can notice that there are responses all over. Play that again. So there are responses pretty much everywhere. So finding a major source of reflection is pretty hard, especially given our cluttered environments, like as you saw here. Pretty much several objects right around the device are at the same distance. So that is why we get oops.
So this naive, you're calling it a naive form of background subtraction. It's only working because the sensor is fixed, correct? So
Absolutely.
if the sensor were moving,
Absolutely.
you would need much more sophisticated.
Yeah, we would need a tracking,
I see.
probably an optical flow or a tracking or particle filtering, something like that.
So you say reflections here and show the positions in meters. What about the speed? Can you detect the speed of the moving object and use this as a help?
Speed, could you please come again?
The speed of the moving object. So from the videos we saw, it's just reflections,
Right.
which is distance,
Right.
the time delay.
Yes.
how well the speed detection worked?
So we were battling down issues with the device until yesterday. So we probably in a couple of days we might be able to really find out how the ambiguity function behaves on this new device. That is,
Because technically, another best criterion for filtering is, okay, everything, subtract everything that doesn't move,
right.
and leave only the moving objects which have speed above the certain threshold, and that will provide a
Yes.
much cleaner image eventually.
Yes. That's exactly what radars make use of, because they basically they have a threshold velocity ranges, and any object that is not moving in that range of velocity is rejected as a noise. So that's what even the radars do. Yeah, so all the post-process, a lot of post-processing is remains. It is yet to be done, and we'll figure out soon how the ambiguity function works in probably a couple of days.
You have 1.5 days.
Yeah, not a couple, 1.5 days. Right. So, sincere thanks to my beloved mentor, Hannes Gamper. He helped me a lot, and none of this would have really happened without his guidance and support. And Dr. Mark Thomas, he gave us several insights during the project to debug several issues with the hardware, for the algorithms, the GUI tools that we saw, the calibration, the impulse response recording, the beamforming tools, all of them were developed by Dr. Mark. And thank you, Dr. Ivan, for your continuous encouragement and ever smiling approach. And sincere thanks to Dr. David Hickerman. Basically, this project came into being because of him. So he wanted this device to be prototyped and tested, and the algorithms to be built. So thank you so much. And especially the hardware lab members, Alex Ching and Jason Goldstein. They really helped us through in and out issues of the hardware, right from development, testing, all of those. That's about it. Thank you so much. Any questions?
So back to the beamformer synthesis for both the loudspeaker array and the microphone array. Did you guys use the phase information? Did you get any phase information, or it was complete noise?
Yes, so the beam matching actually uses both phase and magnitude. But the question is whether we should perhaps ignore the phase in some regions rather than use it for the whole 360 degrees.
I mean the phase response of the transducers.
Yeah. So
another note here is that technically what is interesting to see is the multiplication of those two.
Mm-hmm.
This is the joint directivity pattern of the transmitters and the receiver beam, which actually brings another interesting idea. Can we do a joint synthesis of the transmitting and receiving beamformers in a way to maximize the directivity? We don't have that if we have a big side lobe of the transmitter, if we do have a node there from the receiver.
There was a time when we were deciding what the geometry would be, that we would maybe even interlace, have transmitter, receiver, and arrange them in a way so that we could try to control all these aliasing artifacts.
Mm-hmm.
But it seemed easier to create two independent arrays because the analysis of those arrays was so much more straightforward.
And the other advantage is that by keeping them separate, the microphones could be cramped into 15 millimeters diameter, which
reduces the aliasing. You have a substantially lower aliasing on the microphone array than on the loudspeaker array.
Another thing here is, of course, so we actually measured the impulse responses in the setup he was showing with truncation of the impulse response. And obviously, going to the anechoic chamber might help for calibration purposes. And if we were to move away from the resonance, then perhaps we would also get.
So pretty much from what I saw after calibration, your work range is slightly above the resonance frequency, 45 to 50 kilohertz. You equalize it, the transmitters, you see, the response is flat here. This is your work area. It's not 40 kilohertz, it's here.
Yeah.
Yeah, we'll definitely take that into account and retest, recalibrate. Any more questions?
So I guess I didn't quite understand what is the spatial resolution of objects that you can detect. Like, are we talking mostly about cars and people, or and walls, or anything smaller than that?
Can you increase the volume? I didn't.
Sure. What is the spatial resolution?
Oh, what you mean the
What size objects can you detect? Do you have to look at something the size of a human and larger, or can you look at smaller objects?
So, several factors come into play, like the range at which the objects are, because that decides the resolution. And so, a direct, straightforward answer, a frank answer is we still don't know, because we got the device just about 2.5-3 weeks back, and to get the device set up, calibrated, and get some initial results itself is quite a challenge. But I'm assuming, so our, at least the map resolution is 15 degrees, as you saw. And with regards to how many bins of those map a real world object occupies, we still need to figure that out. We still need to test that.
So at 192 kilohertz, one sample time is around 2 millimeters, 1.8.
Okay.
Theoretically, this is your resolution in distance, practically will be way lower than that. Hey, bats do it. Bats do it.
45 kilohertz is about 8 millimeters.
Yeah. Bats do it.
Okay.
With 45 kilohertz chirps, they can catch an insect.
Yes.
So it's possible.
Yeah, bats.
And by the way, the brain of a bat is not that much more computationally powerful than a modern computer. So
The advantage, I guess, the bat has is that both the bat and the insect are suspended in air.
Fewer reflections, yeah.
If we were to do the same thing.
Well, if you attach the device to a drone, then
Well,
The drone itself might induce some vibrations and.
true.
but the obvious next step would
Straight
be
to a drone.
Yes.
we could certainly take it outside. So this was a setup that was necessitated by the mostly time constraints. But if we were to take this outside and repeat the experiments there, I think we would get rid of a lot of reflections, and then would get perhaps a better idea of how this might perform
So
when there's less.
yeah, and if it's an open space, we would definitely not get such responses. Completely. There's pretty much an object right around the system at very close ranges, and the problem is the human being is just one of these at the same range, so we don't really know. And also the signal to noise ratio is not very great in such a cluttered environment. You don't know whether the human being is reflecting, or it's hitting the human being, hitting a closer object and then coming back. By then the human being might have moved past. Or
you don't even need open space. Ivan Dukmanich used the atrium, which is enough large to basically to be equivalent of open space except the floor.
Yeah.
Right.
Okay.
if there are no
Overall,
more questions.
very good work. You made the progress in that direction.
Thank you.
Thanks for building on top of Ivan's work, and hopefully next year another intern will start to push this further.
Right, sir.
Okay,
Thank you so much.